Here are the different sections in Chapter 1. Within this video, we're going to be looking at towards the end. We'll be looking at some properties that I think you're familiar with, things like volume, mass, density, a problem-solving approach called dimensional analysis, and also pointing you in the direction of significant figures. Different properties, mass, volume, density, what do they correspond to? Mass, that's the amount of matter an object has. Volume, the space that it's occupying. And density would be a ratio of the mass to the volume. Temperature is talking about the motion of matter. It's the average kinetic energy of the particles of matter as they move through space. Different ways that we would then measure these properties. So for mass, we might use a laboratory balance. Oftentimes it will be reported in units of grams, kilograms, milligrams. Volume, well, we might have something like a meter stick or some other ruler. If it's a liquid, we could use volumetric glassware. The units that we want to be familiar with there would be a liter. The next one is a definition that I needed to know. A cubic centimeter is 1 milliliter. This is a set of units that I think bridge from one to another. They're bridging from units of length to a description of the volume. So we want to pay special attention to when we have units that bridge from one to another. So let's memorize that 1 cubic centimeter is 1 milliliter. Another bridge would be that by definition, 2.54 centimeters is precisely 1 inch. So we need that if we're going to now bridge between the metric system and the English system. If we're considering the volume, I want to introduce here the idea of water displacement. So let's say we take a brick. We're going to be measuring the volume of a brick. Let's make it a large brick. So we're going to take the brick and we're going to plop it into a pool of water. Notice how the volume has changed. Initially 100 to 109.78. We're displacing the water and using that to determine the volume of our object. So within that previous video, we saw that the brick had a mass. It occupied a particular volume. We could use those, combine those to get the density. So the common units would be combining the common units that we've seen for mass and volume. Kilograms per liter, gram per mil, gram per cubic centimeter are all descriptions of density. Temperature is measured with a thermometer or some other temperature probe. Units to be familiar with will be the Celsius scale and the Kelvin scale. Recall that the temperature is a reflection of the motion of the matter. Here we see H2O as ice, H2O as a liquid, H2O as a gas. Notice with each of those we are changing the position, so we are changing the potential energy. Let's take the ice and cool it down even more. Notice how the motion of the particles is changing. The temperature is a reflection of that motion. Lower temperature, less motion. Increased temperature, increased motion. You can illustrate that as well with the gas. Increase the temperature, we're increasing the average kinetic energy of the particles as they move through space. That's what the temperature is measuring for us. Energy, well, I've used the words kinetic energy and potential energy to describe energy. Let's recognize that the energy and the temperature are not the same thing. We're going to look more at energy in Chapter 5. Let's wait till then to consider how it's measured and learn more about it. But for now, let's recognize that a common unit is the joule, symbol J. So I've mentioned the temperature scales that we're interested in, Kelvin and Celsius. I need you to be able to convert between the Kelvin scale and the Celsius scale and back and forth. I don't need you to be able to do conversions involving the Fahrenheit scale. Measuring volume, here's some laboratory resources. These are considered volumetric glassware. Note that some of them are used to deliver a particular volume. A burette is used to deliver a variable volume, a pipette, a specific volume. A volumetric flask is used to hold a specific volume. Now, another laboratory piece of glassware you might encounter is a beaker. A beaker is not considered volumetric glassware, however. It certainly can hold a liquid, but you notice it's not in that list of volumetric glassware. What do you think makes something volumetric glassware, and why would a beaker not be considered volumetric glassware? I think you're probably already familiar with the metric system. There's several prefixes that I've introduced. Kilo as in kilogram, centi as in centimeter, milli as in milligram. As we move on in the course and we get more prefixes that are relevant, we'll add those to our repertoire. But for now, let's make sure that we know how to convert between these three metric prefixes: kilo, centi, and milli. Here's an example. Convert 3.70 times 10 to the 7th centimeters to kilometers and express your answer in scientific notation. So stop the video, pause it right now, grab a piece of paper, work through this one, and see if you can do the conversion. This is how I set it up. So I have a certain number of centimeters. I'm going to convert those to meters. 1 meter is 100 centimeters. I'll convert my meters to kilometers. There's 1,000 meters in every 1 kilometer. What I'm doing here is an approach called dimensional analysis. Numerator cancels with denominator. Numerator cancels with denominator in terms of the units until I'm left with the ones that I'm interested in, and I'm expressing that then in scientific notation. Dimensional analysis is a problem-solving approach where we're keeping track of the units and we're using this scheme in order to cancel them and change them. I think dimensional analysis might be something you're familiar with. If you want more information on dimensional analysis, check out the e-text. So this is in chapter 1. There's quite a bit of information, including sample exercises where it works through the example, figures out how to cancel the units. There's even interactive videos that you can watch that illustrate the idea as well. So if you feel like you're not an expert on dimensional analysis, I'd stop the video right now, I'd check out the e-text, and I'd learn more. Here's the dimensional analysis problem. It's involving volume, 1.55 liters to cubic meters. Stop the video, grab a piece of paper, give this question a try. This is what I think we have to accomplish. So if we're looking within the different conversions, does this look like what you have on your piece of paper? We have 1.55 liters. I know in order to bridge, I know that 1 cubic centimeter was defined as 1 milliliter. So if I can somehow convert liters to milliliters, that'll get me to cubic centimeters. And then when I'm in cubic centimeters to meters cubed, that would be this conversion here. My answer is this value right here. If you don't have this value, pause the video, return to your work, see if you can find your error. If we have the right conversion factors, it's going to work out. So we know that for every 1 liter, it's 1,000 milliliters. The key thing that we want to be aware of is this conversion factor right here involving cubic units. 1 meter is 100 centimeters, but we're interested in canceling centimeters cubed. So we need to cube this entire term, cube this entire term. I find it helpful to think about it in terms of an actual cube. 1 meter would be 100 centimeters. That would be one side, but if we're doing centimeters cubed, we need to multiply all three sides together to turn it into cubic units. This right here is the key mistake, or the key thing to look out for when we're seeking to do conversions involving cubic units. Here's another one involving cubic units. So this is combining multiple ideas. Stop the video, see if you can answer this question. This is really typical of what you might encounter on an exam. Okay, another task for you. Let's return to this video where we had our brick. If you recall, we said let's use a large brick. So let's record the data that we see within this video. So the brick has a particular mass, And by displacement, we learn that it has a particular volume. Initial volume, and then the water displacement value. So let's consider this question. A similar brick, meaning it has the same density, shaped like a cube, was then dropped into water. So we repeated the experiment. This raised the water level to 104.35 liters. Two questions for you. What is the mass of this brick in milligrams? Express your answer in scientific notation. And what is the volume of this brick in cubic inches? See if you can work through both of those. These are really good applications for the ideas within this video. One more set of ideas to push you to. So significant figures is a set of guidelines that we use when we're reporting our different measurements. I think this might be a topic you're familiar with. What I'd like you to do is review the concept of significant figures within the e-text. We have the concept itself, but even more importantly, we see that we have different sets of guidelines that we use when we're doing mathematical operations with significant figures. There's one set of guidelines when we're doing addition and subtraction, another set when we're doing multiplication and division. So what I need you to do is become familiar with both sets of rules. How do we handle significant figures when we're doing addition and subtraction? How do we handle it when we're doing multiplication and division? Review those ideas and then try this calculation. Perform this calculation and report it using the correct number of significant figures. So in this video, we've looked at a few properties of matter. I've identified some metric prefixes that I know that you're going to need to be able to manipulate to begin this course. Introduce briefly the idea of dimensional analysis and cautioned you that we need to be careful when we're performing dimensional analysis involving cubic units, and pointed you to the e-text to begin to explore the concept of significant figures. Especially important in significant figures will be the rules that we apply when we're doing calculations.